The title of my talk today is on the coherence of fake news articles, and this is a joint work across the three of us. Iknoor is an undergraduate student who is going to be joining the PhD program at University of Sheffield, and I am with Queen's University in Belfast, and Anoop is a PhD candidate at the University of Calicut in India. And this is a presentation at the workshop on news recommendation and analytics, the abbreviated to INRA 2020. And which is to be held in conjunction with the ECML PKDD 2020 conference in September 2020. So, well, if you have any questions about this talk, please email me at deepak@acm.org. So, fake news is quite well used and well understood term these days, and it came into prominence in 2016 around the time of the US presidential elections. And fake news is generally considered to have a broad spectrum. It starts from deliberate misinterpretations on one hand, misrepresentations on one hand, to sort of mild misunderstandings on the other hand as well, on the other end of the spectrum. But we will use the terminology fake news to refer to intentionally false news. So let's look at data-driven fake news detection. This has been an area which has seen tremendous amounts of activity over the last several years. There are three kinds of features. One is content, one is network, and the third one is propagation. So network as in like the social network structure underlying the fake news ecosystem. It could be like let's say that you're tweeting some content, then you have a social network embedding which is formed by the people whom you follow, the people who follow you, etc. And propagation information is about the likes, the shares, the retweets, and those kinds of things that you get. So, so if you go forward, most work on political fake news on Twitter makes heavy use of network and propagation features, and that is kind of expected because Twitter has a very sparse content footprint. It allows only 140 to 280 characters to be involved in a tweet and so on. So this is expected. However, for domains such as long articles in politics, as well as most fake news on medical and science domains, network and propagation information are sparse because you're talking about a particular medical condition which is not heavily in the public domain at that point. Which is not abundantly occupying the mental space of a lot of people at that point. But so the propagation information is kind of subdued and long drawn across many days or months, and it's not as real time critical as compared to political fake news. And also the content is quite large usually. Typically there is a big text content associated with the fake news. So content is abundant. And also I would like to point out that content is where the fakeness lies. So whether you use network and propagation features to identify fake news, you are in a way looking at the outward symptoms of fake news, whereas the actual fake news lies in the content. So how do we identify fake news in text-heavy domains? One possibility is the conventional supervised approach, where you develop labeled datasets for the domains and train a classifier and deploy it. Right, and deploy it on unseen data, and you get some kind of decisions, and you make use of those decisions. And the alternative approach is to investigate, is to take a more domain-heavy approach to investigate the character of fake news against legitimate news and identify meta-characterizations of the differences that are quite persistent across broad spectrum of fake news and also quite high level. And we develop heuristics that computationally characterize such differences and computationally test whether these lead to statistically significant differences. And if you come up with several of these high-level meta heuristics, they could be put together and batched together to form potentially a fake news detection framework. And the advantages of that fake news detection framework would be that it is driven by a more domain-informed understanding of fake news as compared to letting the machine do the task. We know what features we are using, we can critique it, we can analyze it, understand it, critique it, and all of those things, and we can explicitly avoid spurious correlations. So there is this thing that is employed in many domains where you are heavily data driven, where you don't have much domain understanding, where you kind of put everything. It's like an add and stir approach. You put all the features that you have, all the data that you have into the mix, and then let the algorithm figure it out. And if the algorithm figures it out, it could even figure out things like correlations between the fakeness and the user ID, a particular user ID, which is kind of problematic looking at it from an ethical point of view, because it undermines that user ID's ability to evolve and change with time. People evolve and change with time, right? So excess content will continue to be labeled false if there is a high probability or high if there is a high historical footprint of fake news coming from that ID, and regardless of whether X has changed over time. So it is more generalizable to the changing characteristics of fake news. However, the problem with this is that you are reducing your remit to a small set of dimensions of differences which you can understand, evaluate, and critique, and so on. So you would eventually miss out on certain features that are available in the data. For example, you would not use this user ID feature at all. So it would be hard to approach accuracies of the purely data-driven approach. And that is quite a problem when it comes to publishing, because when you're doing work in this area, it kind of puts the data-driven approach as being easier to publish. So people of course are driven towards that. However, we believe that the alternative approach has quite a lot of merit, and it's also normatively a more correct way of doing things. So our aim is to address this question: is lexical coherence a dimension of difference between fake and legitimate news? So we are asking basically the question whether fake news articles are less coherent. So we would like to address this question computationally. So this is a computational social science endeavor. And what is coherence, right? So that is a central question here. So coherence, in a way, we can kind of say that well, we are addressing the question of how well do the parts of the article fit together, how interconnected are the different parts of the article, how well does the article read as a unified whole, etc. And it's related to the notion of cohesion used in linguistics, and we use the term coherence because it's more familiar to the computing community. Cohesion is not as familiar, and cohesion is considered as an important feature in assessing text quality. There are several references in the paper towards the end of the introduction, so you can maybe feel free to go through those things if you would like to understand what cohesion is. So our objective in statistical terms is to test this hypothesis whether fake news is less coherent, and our null hypothesis is that fake and real news don't differ in coherence. And we would need to, in order to undertake this computational social science study, we would need to identify or quantify coherence, right? And we use three methods or three ways of quantifying coherence. One is text embeddings, the second one is explicit semantic embeddings, and the third one is about entity linking. Explicit semantic analysis, I suppose it's not explicit semantic embeddings, but essentially that's what it comes down to. So the text embedding coherence assessment involves a simple three-part framework. You consider each article as a set of sentences, and each sentence can be represented as a vector, which is formed by the average of the pre-trained word embedding vectors of component words. So you take each of these words, look up their pre-trained word embeddings. We use word-to-vec pre-trained embeddings, and then take the average to form a sentence level vector. And the coherence of the article is simply the average of the pairwise similarities between sentence vectors. And for explicit semantic analysis, we use a similar framework, except that the vectors of sentences, the vectors associated with sentences, are formed by the average of the Wikipedia vectors of the component words. It's not the average of the word-to-vec vectors, but the average of the Wikipedia vectors. You can look at explicit semantic analysis through the references in the paper if you would like to know more details about it. And the coherence is simply the average of the pairwise similarities between sentence vectors. And now coming to entity linking coherence assessment, the third method that we use, each article, now we don't consider each article as a set of sentences, but as a set of the entities it contains. So each entity can be represented as a vector formed by the Wikipedia to vec technique. So you identify entities within the article and you represent each entity as a vector formed by the Wikipedia to vec technique. And the coherence of an article is simply the average of the pairwise similarities between the entity vectors. So we use a number of for each of these things we get a coherence of an article, And if we have two sets of articles, one is fake and one is non-fake, we take the coherence average across all the fake news articles and to get a single unified number. And similarly, we get the average of the vectors of all the article of the coherence scores of articles. Sorry, the average of the coherence scores of all real news articles, and we get a real coherence score. So similarly, the real and fake coherence score can be compared, and it can be compared across each of these three methods of computing coherence, right? So that's what we do. And our data sets used in our experimental evaluation is ISOT fake news, which is quite a popular fake news article data set. It contains articles which have an average of 10 to 15 sentences. And there is also this health and well-being data set, which we curated, and we are making it public as well. So please keep an eye out. So 1K articles, 500 fake and 500 non-fake, and it's all in the health and well-being domain. And it's longer articles, 25 to 30 sentences per article. Okay. So the results that we have are summarized in this table. So for word embedding, if you look at ISOT, you can see that the fake coherence score is 0.54, whereas the legitimate coherence score is 0.56. So it means that there is a difference of 2% or 4% almost across these two coherence scores. And the p-value for that difference is highly significant. The p-value, the lower the better. So this difference is highly significant, highly statistically significant. So similarly, for health and well-being, you have a statistically significant difference, and it's actually an 8% difference in coherence scores for word embedding. And for ESA, the differences are much milder, and some of them are not even statistically significant. And whereas for the entity linking coherence assessments, we again see statistically significant results. However, the difference between the scores are not as much. We have a detailed analysis in the paper. Please feel free to go through that. So the largest difference is observed for the word embedding coherence scores, so which kind of indicates that maybe if you're looking to assess the coherence with an eye on differentiating between fake and real news, you may be better off by using word embedding coherence scores as against DSA and entity linking coherence scores. So the general trend is here. So we're taking one of these data sets and looking at the word embedding, looking at one of the coherence scores and plotting the histogram. So the red bars are associated with the histogram plots of fake news articles, whereas the green bars are associated with real news articles. And as you can see, the fake news coherence scores kind of peak earlier, so at a lower value, as compared to the legitimate news coherence scores. Both of them have a unimodal distribution. However, the fake news coherence scores peak at a lower value of coherence as compared to the legitimate news coherence scores. Right. So the questions is, so essentially we have established that that fake news articles are less coherent, and you can look at more detailed analysis. But this leads us on to several other questions. Why are fake news articles less coherent? Is it because they are produced by inexperienced media houses? Is it because they use multiple sub-stories? Is it because they mix emotional and factual narratives? And also this interesting question that came to mind maybe last week on seeing a Guardian article is, would technologies like GPT-3 generate more coherent fake news? Right. So there was a Guardian article which was written entirely by robots, and I think it would be an interesting analysis to see what the lexical coherence of this article is. But the broader question is, would technologies like GPT-3 be able to generate more human-like and more coherent fake news? And so how do they rank in terms of coherence? So that brings me to the end of this presentation. We have a book coming up on data science for fake news, which contains a lot of surveys and perspectives of interdisciplinary analysis of fake news. And in fact, in particular, I've written two chapters in it. One is on unsupervised methods, and the second one is on ethical considerations. And I would be happy to send these chapters to any of you who are interested, if you would like to catch a glimpse of it. But essentially, I just wanted to bring that up to basically promote this book in a way. So if you have any questions about this presentation, please feel free to contact me at deepak@ecml.org. So that brings me to the end of this presentation. Thank you.